Okay. For realsies this time. System input function characteristics. So, chapter 8. We will consider only deterministic inputs for now. These can be grouped into two categories. What do I mean by deterministic inputs?
Cause and effect.
Yeah. There are a couple of things that can mean. So I don't believe that we will consider at any point this semester noise coming in, but randomness. So nothing random, no random signals going in. Deterministic signals are signals that are that have a coherent structure to them, unlike a noisy signal. But a deterministic system, which we're not going to really talk about, but since we're feeling like sort of we're flitting around everywhere today, we might as well talk about it for just a second. No, we're not going to. I'm going to come back. All right, so we're going to consider two different categories of deterministic signals. Aperiodic, or transient, signals, then they are inputs. They are functions that are not repetitive. Or two, the other type, is periodic. Functions that repeat at regular intervals, t. So, for instance, the function is equal to itself on every multiple of t. So, where n is a non-negative integer, multiples of the period, what do we call that? T, period? Yeah, call it the period. We'll get back to periodic functions in just a moment, but we're going to start out with an aperiodic function. So the unit impulse function, probably the most surprising of the functions we're going to consider. You guys, has anybody seen this, the Dirac delta function? Yeah, a couple of you? All right, so let's consider this function, which is not the Dirac delta function yet. It's 0 for time less than 0. Okay, so on this graph here, it's 0. And then it's 1 over big T for the period from 0 to big T. So I drew 4 different cases here, but let's take the green one. So T1. So 1 over, it would have height 1 over T1, and it would have width T1. And so what is the area of that rectangle?
T1 times whatever.
Times 1 over T, right? 1 over T1. So it's just 1, right? Because they cancel. We constructed the area to always be 1. And then 0 again afterwards. So the Dirac delta function is defined to be, we just use delta of t. It's defined to be the limit as big T goes to 0 of delta t of t, where delta t of t is this function up there. So what does that mean? If big T goes to 0, it means the width is getting smaller and smaller. So it's going from like green to orange to purple to blue, and we're just getting thinner and thinner and thinner, right? And what happens to the height? Yeah, so it has infinitely thin width and infinitely peaky height. And we're left with something, and we can't draw that, right? So we just represent this as being a line with an arrow, okay? But the interesting thing about this is that the area is always just 1, okay? Area under the curve is 1. Technically, it is not defined at 0. So its value is 0, 0, 0, 0. And then it approaches infinity here, right? It approaches infinity, which, you could say undefined, or you could say approaches infinity, and 0, 0, 0, 0, okay? You might think, gosh, that's a very strange function. How is this going to be useful? You're just going to have to believe me for now. I'll show you later how it's useful. An important property of this Dirac delta function is that the integral over its entire range, domain, I guess, is 1. And it has 0 width in the limit and infinite height. We can scale it like this. We can multiply some constant k by delta, which has area k then, right? Still has infinite height and 0 width, but it has area k. Because if you integrate over it, instead of being 1, you're going to have k times 1. Okay? We call that scaling factor the strength. We represent the strength by changing the length of the arrow. So if you have a regular Dirac delta, we usually just draw it up to height of 1, even though it has a height of infinite, but we say it has an area of 1, so we draw it up to 1. It has an area of 2, or a strength of 2. We draw it up to 2, etc. Impulses approximate sudden, short inputs, like a hammer strike, okay? Obviously, hammer strikes aren't exactly an impulse, but they're surprisingly good at, impulses are surprisingly good at approximating things like that, sudden impact, sudden spikes in things. And we use them, we like to use them because analytically they have these really nice properties, and they're really nice to integrate over. There's this thing called the sifting property of Dirac's delta function that's pretty great, and you can look it up on Wikipedia. It's a very useful little property. We don't need to go into it right now, though. The unit step function is the next one. So the unit step function, or also called the Heaviside step function, is defined as us of t, defined as the integral from negative infinity to t of the Dirac delta function. Yeah, right? So, I should make a nice box around that one too. So, this kind of makes sense, right? So the way to interpret this is we're going to integrate this, and we're going to go along. The area is 0, the area is 0, the area is 0, and then, oh, what's the area now? 1, right? Because once it goes over this hump, all of the area under this happens at 0, right? So from 0 to 1, and then it's just, there's no more area to be picked up, right? So just 1, 1, 1, 1. So that's the unit step function. Means that it's 0 for all time is less than, or by convention equal to 0, and then it's 1 for all time greater than 0. All right. Unit step functions are often scaled with a constant like k times the us. That would be like, if it was 5 us, it would be height of 5. All right. How do we feel about that stuff so far? Pretty straightforward. Unit ramp function is defined as, do you guys want to make a guess? I'm entertaining guesses.
You are
T negative. Anyways. We're
Yeah.
already writing.
This to what? Over what?
US.
Yeah. Unit step function. Okay. And I could make a cool box on that too because I have that capacity. Now, if you were to integrate this, 0, 0, 0, now we start adding little bits of area, right? And if you integrate a constant, it gives you a straight line that has some slope. So there's our slope. It looks like that. Pretty straightforward. This one's used the least, I would say, the unit ramp. The first two are used a lot. Ramp's used less. The integral relationships above imply differential relationships, where defined. So let's look at this. The way that we often think about it is that the Dirac delta function, we went on this side of the loop, right? We integrated. S to the minus 1 means integral operator, right? So this is a little block diagram. Like that. So there we go. Delta goes to unit step goes to unit ramp. You could also differentiate unit ramp goes to unit step goes to Dirac delta function. So these are typically called the singularity inputs. I didn't use that term, but the book uses that term, singularity inputs. Very useful. We use them a lot. And we'll be using them for the next rest of your career. Sinusoidal inputs, we know these well, right? So we've already covered them. I'm not going to go into the details. We can recognize and label these things in the graph, right? So the amplitude, this is the period, this is the phase shift, right? And finally, exponential inputs. An exponential input, e to the st, where s is a complex number, sigma plus j omega, can describe a number of complex inputs, including sinusoidal inputs, which you get if you say that the real part of this complex number is equal to 0. A real exponential, which is omega equal to 0, and mixed. So you could have a decaying exponential or an increasing exponential. In general, you can take this and separate out the real part from the imaginary part. And you can use one of Euler's formulas to write this identity here and see that you have a sort of a sinusoidal term, and then you have an exponential term, or a real exponential term. Okay, so we've used Euler's formula here. Here are some useful implications of Euler's formula. I've already given you guys these before, and we've used them a little bit, but it's kind of nice to have all these in one spot, all the inputs that we might use in one spot, so I just listed it again. So, you guys remember that part where we were doing phasors? We've covered a lot of material. That map just makes it seem so small. This is a very high view that we took. All right. So I'm actually, believe it or not, going to cover all 3 pages, I think it is, of the next one in the next 4 minutes.
Do it. Go.
Watch this. So all that we're doing is I'm just looking at this and I'm saying, this looks familiar. This is the differential equations handout that I gave you. You guys already know all of this stuff. Gasp. Oh my, that's great, right? So the state space representation is the way we like to model things, right? but we can also write it in this classical input-output, single input, single output form, which, if we go back to our map, is going from state space through the transfer operator to the input-output differential equation, right? That's where we're at. Then we know how to define, so I'm going to leave these notes up there. The forcing function is what we call whatever the right-hand side is of the input-output differential equation. Okay? So everything over here that has to do with an input or a derivative of an input ends up on the right-hand side. It's convenient to write this in this form. Now, I go through the existence and uniqueness theorem, which says that given this, there is a solution exists, and it's unique, meaning there's only one. So you can't say that there are other answers to it. There are not. It also says that you can come up with a general or total solution by summing the homogeneous and particular solutions. Yeah, I know, right? Shocking. I know. Homogeneous solution, it goes through how to do that. How to do the homogeneous solution. Even gives you a nice little example. A particular solution, we're using the method of undetermined coefficients. Here's how to do that. General solution, you add them together, and there's an example. So that is lecture 50. Totally review in case you have forgotten how to solve differential equations using the method of undetermined coefficients. Because guess what, guys? It's coming back again. It's coming back. So, all right, I'll see you guys on Wednesday. I guess you guys want your exams?